Hi everyone, today we are going to look at simple harmonic motion. A quick introduction to it, especially focusing on simple harmonic motion with respect to time. And we will look at simple harmonic motion with respect to displacement later on. So firstly, some quick introduction. The simple harmonic motion describes a undampened oscillation. So imagine your favorite environment, the frictionless vacuum, and we have a mass attached to a spring. Because there is no resistance, there is no friction, there's no energy loss in the springs. So once the mass starts moving, once you give it a nudge, it will just go back and forth and forever and ever and ever. So that's the undampened oscillation. Of course, if it's dampened, then it will gradually move like less and less and less, and eventually comes to a stop. But that's not what we're looking at. We just imagine that there's no loss and it just goes on forever. We're also going to look at how this is really a solution to the second order differential equation. We're not going to actually solve it. We're just going to have a quick look at how this comes about. And then we're also going to look at the most common expression of simple harmonic motion, which is a sinusoidal function of time with a bunch of different transformations applied. And also we're going to look at how simple harmonic motion is really the one-dimensional shadow of a circular motion. And in the end, we're also going to try a few exercises, examples to see how the various aspects of simple harmonic motions can be applied. Now let's look at this particular differential equation. So we have x double dot equals to negative k over m times x. So this differential equation is the result of the application of two laws in physics. So firstly, it's the Hooke's law. The idea is where you have a oscillator attached to a spring and just moves back and forth. And imagine if we have a neutral position where the mass would be when it's at rest. Then the force here is proportional to the opposite of the displacement. Linking that to your normal experience, if you have a spring, the harder you pull it, so the longer you stretch it or the more you compress it, the more force the spring will exert to fight against that. So what it means is the more in our diagram, the more you stretch the mass, the more it moves towards the right, the more force the spring will exert to the left, pulling it back. That's what Hooke's law expresses. The more you stretch the spring or compress spring one way, the more force the spring will exert in the opposite direction. Next one, Newton's second law of motion. Everyone knows it, everyone loves it, and so on. Yep. Okay, now if we combine the two, because they're both describing the force in the same system, so we can either describe in terms of the spring or the spring's displacement, or we can describe in terms of mass and acceleration of the oscillating body. So if we put them together, negative kx equals to mx dot. What we end up with is, let's rearrange things, x double dot equals to negative k over mx. So in most cases, K and M remain constant. Basically, K is the stiffness of the spring. So it tells you the stiffer the spring, the larger the K, which means the more you stretch it, greater the force will acting in the opposite direction. So K is usually called the spring constant. It describes the stiffness of the spring, and M, mass. Yeah, it's just the mass. So K and M, we like in idealized systems, they just the constant, and in this sort of problem, we assume they are constant. So we can represent negative K over M, or rather, actually, just K over M. We just represent K over M with a single constant, which is the big K. So we can represent the whole thing with negative Kx. All right, so this is the differential equation. This just tells us the second derivative of a specific function x. Well, they're both functions of time. So the second time derivative of x is equal to minus k times original function. So our function, the one we are looking for, is proportional to the opposite of the original. The second derivative is proportional to the opposite of original. So which class of functions can be used as a solution for this differential equation? We're not actually going to solve this, but I did make a video early on how to solve a differential equation like this, so check it out if you really want to know. But just by eyeballing it, we can tell that sinusoidal functions satisfy this, because if you think about it, cosine, if x equals to cosine t, because they're both function of time, then x dot equal to negative sine t, and of course x double dot will be negative cosine t. As you can see here, the second derivative is proportional to the opposite of the original. Or of course, we can also say that if different transformations apply to this. So if we say if x equals to sine nt plus whatever the value here is, so, and then x dot would be equal to negative cosine nt plus phi, and of course x double dot will be negative n square sine nt plus phi. Yeah. So as you can see here, because n is a number, so the second derivative is still negatively proportional to the original function. Yep. So that's the gist of the solutions to a function like this. Sorry, a differential equation like this. So sinusoidal, that's where the simple harmonic motion equations we'll look at comes from. Now let's have a look at this equation in some detail. Okay, I'm sure most of you are familiar with the kind of transformations being applied here. So A, obviously, it's the amplitude, because the maximum value a cosine function can give out is 1. So A multiplied just increases the maximum and the minimum values of the function. So this is the amplitude. And if we want to graph it, it represents the maximum and the minimum, maximum or the minimum to the neutral position. Next one, n. Well, n times t, because t is the variable here, this multiplies the variable. And in a lot of places, you will see this is called angular velocity because it basically tells us how fast the function completes the cycles. And a lot of places, you will also see it written as omega. So angular velocity. And then phi here is, of course, the initial phase, because this is what this function takes on when t equals to 0. So when t equals 0, all that is left inside this parentheses is phi. So phi is the initial phase. So that determines the initial value of x. Oh, like phase. And of course, C is where the neutral position is, where the center is. Okay. So if we look at this function in some detail in this GeoGebra thingy I prepared earlier, as you can see, we vary A, the amplitude changes, small a, lower troughs, lower peaks, shallower troughs, and so on. Yeah. If I vary n, if I vary the angular velocity, what we end up is, say right now the angular velocity is 2. That means it completes 2 cycles in the duration of 2 pi. Yeah, so as you can see here, as you can see here, this is the cosine wave, and in the distance of 2 pi, it completes 2 cycles. So if we increase n to 3, as you can see here, in the space of 2 pi, it completes 2, 3 cycles. Yep. So it basically just tells you in a span of 2 pi how many cycles how many cycles is completed by our function. Of course, phi is the initial phase. By varying it, we can vary the initial starting position. So either way, we're just moving away from let's say when we have 0, as you can see, our function is perfectly centered, and by moving it, the function shifts. And of course, the last one, the constant, the center, just determines where the center of the function is. As you can see here, when we have c equals to 0, our whatever it is oscillates about 0, but if we increase it to 1, then our object oscillates about 1. So it goes with amplitude 1.2 up, 1.2 down, 1.2 up, 1.2 down, and so on. Okay, next one. Yeah, so that's the gist of this function and what all the constant terms do in this particular expression. And finally, let's have a look at how, as I mentioned earlier, how to see the simple harmonic motion as the one-dimensional shadow of a circular motion. So imagine we have a circle. Now, just watch point P and its vertical value. Yeah. So as you can see here, let's make everything disappear. So if we have our rotation here, we can just say P rotating about a circle. Yeah, so this is very basic circular motion. So P just moves around to like 720 degrees. Yeah, 2 revolutions around the circle. Now, what would happen if we only look at the vertical component? So let's look at a second point, Q, where it's dependent on P for its vertical component. So as P increases, Q increases. But at the same time, the horizontal component of Q is the angle here. So I guess rather than having a cyclic motion going through a circle, we laid the angle flat, and if we trace the trajectory of the Q, as you can see, as P increases, remember the only thing Q depends on P is its vertical position. So as you can see here, as we trace it through, as P rotates, Q plots out a sine curve. So if we go stretch it further, yeah, basically, what's happening is as the P goes through the circular motion, if you look from the side on, all you can see is its y value increasing to a certain point and decrease and then cycle through. So if we can only look at one-dimension movement, then one of the components of this point P moving in a circle will end up representing a simple harmonic motion. So that's the idea. Okay, now that's the theory part done. Let's have a look at some examples. Let's look at this pretty straightforward example. Everything's already given to us. So we have we have basically a particle moving with the equation of the motion already provided. So we just have to eyeball this, write down this, and find the center, the amplitude, and extremes of displacement. Yeah, so what does the 3 do? So imagine if we have the function, 3 just shift everything up by 3 units, yeah? Which means that with the amplitude of 2, it goes 2 above and 2 below, isn't it? And then it means that however the wave moves, the particle moves, it will be going to 5 and between 5 and 1, isn't it? So 2 above 3, 2 below 3. So we can just write as A, the center equals to 3, amplitude equals to 2, and extremes of displacement, basically its maximum is 5 and minimum equals to 1. Okay, secondly, we're going to look at the period. So the period is basically the distance between the 2 troughs or 2 peaks in this case. So we want to find out basically how wide this wave is. So what the distance between 2 peaks is. Okay. Now this is the part where we have to utilize this number here. So remember the multiplier of t. That's the angular velocity. That's how many cycles. So that how many cycles are performed in the span of 2 pi. So we can basically write the period as 2 pi over n. Yeah, because of n cycles in the a period of a span of 2 pi, and that will give us the width of each cycle. And in our specific case, n equals to pi on 2, so t equals to 2 pi divided by pi on 2, and that gives us 4. So that is the period. Each cycle has a width of 4 units. And actually, initial phase and location. So when t equals to 0, obviously the first part disappears. So it's just so the phase is just pi on 6. And for the location at t equals to 0, so obviously x initial position equals to 2 sine. Of course, this whole thing collapses, just pi on 6 plus 3, so x0. Pi on 6, that's 30 degrees, that's a half, so 2 times a half equals to 1 plus 3 equals to 4. So that gives us the initial location. And then next time, when the particle is at the same position, so so what we have to do is we also have to find out what's the next time the particle has a displacement of 4 again. So we have 4 equals to 2 sine pi over 2t plus pi over 6 plus 3. Okay, so we have to solve for t in this equation. So obviously 4 minus 3 is 1, 1 divided by 2 is a half equals to sine pi over 2t plus pi on 6. And of course, we end up with pi on 2t plus pi over 6 equals to, obviously, we can just get the, what should we call it, the inverse. So sine inverse of a half, obviously the first one is pi over 6, but it's not very helpful because that is our initial position. Yeah, pi on 6, that's already our initial position. So what we need to find is the next one. Okay, what does that mean? It means if the first one is here, then we have to find this is where we have the same sine value. Okay, so fortunately, we can say this is just 2 pi minus okay, so this is just 2 pi minus pi on 6. Sorry, not 2 pi, pi minus pi on 6. So this one will be 5 pi on 6. Yeah, so this is actually what we're looking for. This one we don't have to worry about because that's just the initial position. So we look at pi over 2t equals to 5 pi on 6. Of course, t equals to multiply by 2 on pi. That gives us 4/3. Yeah. So when t equals to 4 over 3, the x value becomes 4 again. So the particle is at the initial position. So basically the idea is starting here. All right, that's bad. Okay, so initially the particle was here, and then after cycle when t equals to 4/3, we get 4 again. And yeah, that's pretty much it. Now let's look at a second example. It's also pretty straightforward. Our weight is hung from a stand on a table by a spring set in vertical motion. The weight oscillates between 15 centimeters and 35 centimeters above the table and takes 2 seconds to complete one cycle. Yeah? So there's some information we can gather from the description here. Okay, so firstly, the oscillation is between 15 and 35 centimeters. What does that mean? It means if we have lowest position of 15 and highest position of 35, we have a neutral position here, so it's 10 above and 10 below. Yeah. Okay, so that's the amplitude. However, if we look at the question A, then it hasn't given us really initial time frame, so we might as well start counting at the lowest point. So we might as well count at this point here and then goes up. Yep. Of course, this means that our initial position is negative. So so it might be more convenient for us to have A equals to -10. Or rather, our amplitude doesn't change, but so we rather have a negative A, which equals to -10. Okay, so this is what we have. Now let's look at the period. So period equals to 2, and of course period is equal to the 2 pi divided by angular velocity. So basically how many cycles there is. So what we end up with is 2 equals to 2 pi divided by n, and of course n equals to pi here. So that's our angular velocity. This is the amplitude. So if we plug everything into the equation of x equals to a cosine nt plus, actually, we don't have to worry about initial phase because we can just take the lowest point as t equals to 0. So we end up with x equals to -10 cosine pi t. Okay. And then 3/4 of a second. So at t equals to 3/4 of a second after the lowest point. Do you remember the lowest point? What we have? We're using the lowest point. We're using the initial position as lowest point. Sorry, we're using the lowest point as the initial position. So 3/4 of a second passes, and we want to figure out where that thing is. Yep. Oh, it's not drawn to scale anyway. So that's what we need. So what we can do is actually, you know what? It's not. It's probably closer to the It'll be somewhere here because the whole thing has a period of 2, and then this will be 1. So 3/4 somewhere here. Yep. Okay, so we want to find the height. Now 3/4 of a second. Okay, we need to get substitute t equals to 3 over 4 into the equation here. So x equals to negative 10 cosine 3 pi over 4. And that just gives us yeah, it's this one. So it's negative 1 over root 2. So x equals to negative 10 times negative 1 over root 2. So x equals to 10 over root 2. But of course, do remember this is the distance from the neutral positions. To find the actual height, you have to add here, which is 25, add 25 to it. Yeah, because x value is just how far it was from the neutral. The height from the table, you have to add the height of neutral position into it as well. Okay. Next one, let's look at B. How long in each cycle is the weight at or below 18 centimeters? So below 18, above 8, below 18 centimeters. So 18 is somewhere here, yeah, which is actually 7 centimeters below. So we're actually looking for where the x is at or below 7 centimeters from the neutral position. So we are looking for positions where negative 10 cosine, where negative 7, because negative 7 below, negative 7 equals to negative 10 cosine pi t. And we have to solve for t because for these values, what we need, it will give us is the t positions where the whole thing equals to negative 7, where x equals to negative 7. So 0.7 equals to cosine pi t, and then cosine of inverse cosine of 0.7 is 0.795 equals to pi t, and then t equals to 0.795 divided by pi is negative 0.253. Okay, so positive. My bad. So positive, so 0.795 divided by pi is 0.253. Okay, so it's basically it's here, yep. But the time in each cycle where it's below 18, yep. So of course, that means this cycle we're looking at now, we want to find this portion as well. So of course this is symmetric. So we can just say, well, the other one is if this is 0.253 from 0, so this will be 0.253 as well. So the time spent will be just 0.253 plus 0.253, because you remember it's symmetric. Here 0 to 0.253, then this should have the same width as this. So that will give us approximately 0.51 seconds. Okay, let's look at the next one where we start to involve the velocity of the motion. So an object is in simple harmonic motion with a period of pi over 3 seconds. At a certain moment, it's positioned at 3 centimeters above the center of motion, and it is moving towards the center of motion with speed of 24 centimeters per second. Okay, so basically we can just pick this as our starting point, where the particle is, or the object is 3 centimeters above the center and is traveling at a speed of 24 centimeters per second. So what's happening is we are having a, say this is neutral axis. Yeah, so let's say this is 3, yep. And then it's traveling downwards at 24 centimeters per second. So it's traveling downwards. Okay, but we don't actually know the overall shape of the curve yet because we don't have that information. But we do. But what we do have is the period. Yep. So period is pi over 3. So t equals to pi over 3. And then we can also say we can find what n is. Yep. So basically pi over 3 equals to pi on 2 pi divided by n, which means n equals to 6. Okay, so this is the first piece of information we get. Yeah, so we have x equals to, unfortunately we don't have the amplitude because we don't actually know if 3 is at the maximum or not. So we cannot simply assume 3 is our amplitude. So we just have to write a number to stand in. Alright, but we do have the angular velocity, so which is 6t we just worked out, and then plus we don't know the phase shift either, so that's all the information we have. And then if we plug initial values at t equals to 0, so we end up with 3 equals to a cosine 0 plus phi, so 3 equals to a cosine phi. Alright, that's one equation with 2 unknowns, which is not very helpful at all. So what we need to do now is utilize the information with respect to the speed. Okay, speed or velocity is essentially the first time derivative of displacement. So x dot equals to 6a sine. Actually, cosine differentiate to sine, it's negative. So negative 6a sine 6t plus phi. And then where t equals to 0, the speed is negative 24. So negative 24 equals to negative 6a sine 6 times 0 plus phi. Okay, so what we end up with is negative 24 divided by, so 4 equals to a sine phi. Okay, That's good because now we have two equations. We have 4 equals to a sine phi and 3 equals to a cosine phi. Now to find a, we can simply square both of them. So 4 squared plus 3 squared equals to a squared times sine squared phi plus cosine squared phi. You may recognize trig identity. This is 1. So we end up with 4, 16, 25 equals to a square. So a equals to 5. Yeah, negative 5 we don't have to worry about because amplitude is an absolute value. Okay, next one we need to find what the phi is. So that's also pretty straightforward. We simply divide these two equations. So 4 over 3 equals to a sine phi over a cosine phi. So 4 over 3 equals to tangent phi. And then phi is approximately tan inverse of 4 over 3 is 0.9273. Okay, what about the others? We don't have to worry about it because as we can see here, both sine and cosine have to be positive, which means we're only dealing with the first quadrant. Yeah, so we don't have to worry about the other tangent value anywhere else. Okay, so that's what we have. So we can assemble now all the information. We can just say, well, x equals to a is 5, cosine 6t plus 0.9273. Yeah, and of course we can also do the same for velocity or speed. So x dot equals to negative 30 sine 60 plus 0.9273. That's it. So now we have equation of motion, and of course last one, maximum speed. Maximum speed occurs where this portion equals to 1. Yeah. So maximum speed is basically just absolute value of our velocity, maximum velocity. Yeah, so it's equals to 30 centimeters per second. And that's it. Now, let's look at the next part. So next part where it has the same displacement again. So remember, initial displacement is at 3. So we need to find t where x equals to 3 again. Okay, so what we need to solve is, let's look at equation of displacement again, which is x equals to 5 cosine 6t plus 0.9273, and of course when x equals to 3, so equals to 5 cosine 6t plus 0.9273, and we end up with so we end up with 3 over 5 equals, we end up with 6t plus 0.9273 equals to 3 divided by 5 cosine inverse inverse of 3 over 5. Okay, now we have to find out, we have to solve this equation for t. So what are the values? So 6t plus 0.9273 equals to, so if you punch this in your calculator, you're just gonna go get 0.9273 directly, which is not very helpful because this is in fact the value, the angle of the the initial position, because if you subtract this, you get 0, 6t equals to 0, t equals to 0. So we need to find the second position. So just imagine the next time. Okay, so basically that means initially initially it looks like this. Yep. So this is 3. So we need to actually find this point. So to do that, we need to find the second value for cosine 3 over 5, which is inverse. So the first one is 0.9273. The second one will be, because cosine, so it will be 2 pi minus 0.9273. So we end up with 6t plus, okay, so this value will be 2 pi minus 0.9273 is 5.3559, and that's the value we want. So 6t plus 0.9273 equals to 5.3559, and then 6t equals to subtract is approximately so it's approximately 682.4 point, and then we divide both sides by 6, so it's approximately 0.738 seconds. Okay, so initially this is 0, the next time will be 3 is 0.738 seconds, and that's it. Next, we're gonna look at an alternative expression of simple harmonic motion. So something in this form. Of course, if you really think about it, it's exactly the same format, just written. Sorry, it's exactly the same thing, just written in a slightly different format. Because look at this a, these two constant terms a and b here. Then we can imagine a triangle AB, and then there's an angle phi here. Of course, this edge will just be a squared plus b squared. Let's call it r. Yeah. Okay. So what does r? So what does a equal to? A is cosine, isn't it? R cosine phi, and B is R sine phi. So if we substitute back into this original equation, so it's all the auxiliary equation again. So we end up with x equals to R cosine phi cosine nt plus R sine phi sine nt. Yeah. So and then remember your trig identity. This is just the product to some products. Doesn't matter. So we can just rewrite it as a r cosine nt minus phi. Yep. So it's exactly the same. But sometimes, okay, so sometimes it's convenient to write it into the format we saw before. But sometimes it's also easier to approach the question directly in this format. So let's look at the next example. Okay, so it's the same object as the last example. What happened here? Yeah. So everything else still stays the same, but now the variables are slightly different because we have to look at it this way. Okay. So we need to find A and B. Let's look at let's find what A and B are first. We already know N from the previous one, obviously. N was 6. Yep. So N was 6 from the previous. It's now what's A? So how do we find A? Let's say when t equals to 0, we have x equals to 3, which means 3 equals to A times cosine 6t. Actually, sorry, it's not really t because it's 6 times 0. Plus B sine 6 times 0. Okay, so cosine of 0 equals to 1, and the B times sine of 0 is 0, so 3 just equals to A. Yeah, because this becomes 1, this part disappears. So that's how we find A. So how do we find B? Well, what we can do is we can also use the velocity. So x equals to A cosine nt plus B sine nt. Then the time derivative will be negative and A sine nt plus and B cosine nt. Okay, so with that, we can say that when t equals to 0 and x dot equals to negative 24, then we can just substitute everything in. Negative 24 equals to negative 6a sine 0 plus 6b b cosine 0. Okay, as you can see here, sine 0, this part disappears, so all we end up with is just negative 24 equals to 6b, so b equals to negative 4. And to write everything in this format, we just end up with x equals to 3 cosine 6t minus 4 sine 6t, and that's our equation in this format. Yeah. And then next one, the one convenient thing about writing in this cosine and sine format is that you can use your half angle substitutions relatively easily. So we have x equals to 3 cosine 6t minus 4 sine 6t. And then what will half angle be? Well, the half angle, so let's take tan equals to, let's say this 6t as a whole angle, 6t, yeah, then tan 3t will equal to, we already used t, so we'll have to use tau. Okay. So that's what we have. Now let's do the substitution. If tan 3t equals to tau, that means cosine 6t will equal to 1 minus tau squared over 1 plus tau squared, and then sine 6t would equal to 2 over 1 plus tau squared. Okay, so this is what we have. Now, we just have to substitute everything back into the equation in order to find out where it's at its initial position again. So where x equals to 3 again. Yeah, so we substitute these back in. So we end up with 3 equals to 3 times 1 minus tau squared over 1 plus tau squared minus 4 times 2 over 1 plus tau squared. Okay, so what do we end up with? We end up with we can just multiply both sides by 1 plus tau squared, so it's 3 plus 3 tau tau squared equals to 3 minus 3 tau squared minus 8. Okay. Oh wait, sorry, it's 2 tau here. Yeah. 8 tau. So 3 minus 3 tau squared minus 8. If we rearrange things, 3 cancel out. So we end up with 6 tau squared plus 8 tau equals to 0, which means we have 2 tau uh 3 tau plus 4 equals to 0, which means tau 0 or tau equals to negative 4 over 3. Okay, which is once again tangent of 3t. Of course, what we end up with is tangent 3t equals to negative 4, 3. So 3t equals to tan inverse of negative 4 over 3. Of course, the first answer we'll receive once again is negative 0.9273. However, this is not going to help us much because this is in fact the initial position where t equals to 0. Yeah, because if this is 0, 0 divided by 3, t equals to 0. So we have to find the next one where the second place where the tangent value is 4 over 3. And just imagine here, negative 4 negative 9. So it's basically this one, negative 0.9273. And what we need is to actually find this one. Okay, so what is this one? So this is just negative 0.9273 plus pi, isn't it? So then that gives a value of 2.2143. Yeah, so this is what we want. And of course, divide both sides by 3, so t is approximately 0.738, which conveniently is the same as the previous one. And so there is that.